Okay, so welcome back. We're going to talk about interactions today, and just to recap what we were doing since last time. So last week, first we looked at flows at low Reynolds number, what their properties are, how they're very different from the flows that we see around us. That was one lecture. And the last lecture, we started looking at dynamics or locomotion of microorganisms. And we figured out, because of the constraints or because of the strangeness of this whole world of low Reynolds number, there are certain things or certain constraints on how you can swim in this sort of fluids. One of them was this scallop theorem, where you cannot swim with one hinge. You cannot just open and close. Time doesn't play a role, and so you need to use some other mechanisms. We saw a few of those. One was this waving of an elastic sheet. So essentially you have a flagella, which is an elastic object. You're propagating some sort of traveling waves on it, and that breaks what's known as the time reversal symmetry in the problem, and that helps you swim. And then we also saw that if you have a rigid helix, but you can rotate it, and then also you can break this time reversal symmetry. So that's what we were doing roughly last time. The idea would be that, or the point that I'm trying to make today is, it's great to study single organisms. It gives us a lot of insight on how one things move, but in biology, oftentimes things are not in isolation. They often come in collection. And we are going to make our first step towards understanding how things behave in collection. Okay. And typically when you say, or when you think about collection, you think about very large numbers, large n limit kind of scenario. But the most obvious thing, if you've done the one swimmer system, you want to go to a large n system, is to do a pair problem, right? You want to understand how two things interact, talk to each other. And there is really a wide variety and wide class of problems for pair interactions. I'm going to focus on one thing that I thought would be sort of interesting to look at in the context of what we have learned so far, and that's the question of synchronization. Okay. So that's where I would start from today. So let me just give some background and motivation. What you're seeing over here is an unicellular microorganism called Paramecium. Okay, it's roughly hundreds of microns long or large. And the cell surface, as you can see, this boundary is coated by thin hair-like filaments. Okay, so these are exactly like the sort of traveling wave sheets that we talked about last time, but the only difference is that they are anchored, they're attached to the surface, and it's not, when we're talking about the last time, the flagella, we're thinking about one sheet or one filament swimming in the fluid. Here they are just attached to the surface. And what they do is that they consume chemical energy, or ATP if you would like, and they continuously beat on this surface. And what they do is that, you see that there are thousands of these guys, and what they form is this beautiful traveling wave. Now these sort of waves that you see also help in locomotion of this microorganism, also help sometimes in feeding and so on. But these waves are very reminiscent of things that you observe on wheat fields or grass fields. So if you go to a grass field on a windy day, there is wind blowing, and you observe these sort of waves propagating on the surface of the wheat fields, and these are very reminiscent of these things. But now I want to highlight that there is a fundamental difference between this problem and this one over here. So this is also a very complicated problem. I'm not saying that it's not complicated, but there is a fundamental difference. And the difference is that here, the grass itself is not beating. Okay? So if there is no wind, the grass is just going to stay there, not do anything. And you are driving the system externally by some external field here in this case. In this case, it's wind. And through driving the system externally, of course, you induce interactions between all this grass, filaments, and that forms, or eventually forms, these sort of traveling wave patterns. On the other hand, in the example over here, let me play the movie again. These sort of waves are formed spontaneously. So each filament is actuated internally, they're consuming energy, they're beating spontaneously. So what they're doing by beating is that they're stirring the fluid outside them. So if I'm a swimmer, if I'm a filament moving in a fluid or just waving my arms, I'm going to stir the fluid, right? And now this fluid these flows get communicated across this surface. So they're all interacting through the flows that they're generating. And through these interactions, they spontaneously form this state. That's sort of the hypothesis, yes?
They're independent, right? So if you stop, force one, like a certain section.
So right, so they are all independent objects, they're consuming energy, but remember, there is, even though they're independent, they could be coupled mechanically. So for example, just think of the setup. I will sort of hammer this point later on again. Think about it this way, that you are in a swimming pool and you're moving, okay? You're swimming. So you're generating a flow field. And now you're in isolation, but now suppose there is another swimmer going sidewise, okay? Now you're going to feel that person even though you are independent. And what can happen is that if that swimmer is swimming very fast or going opposite to you, your motion or your dynamics can get affected, okay? So they are independent, but they're communicating or coupled through the flows that they're generating. And together they form this beautiful collective phenomena, which is called metachronal waves. Now these sort of waves are also seen inside our lungs. Okay? So every time you take a breath, you bring in all sort of pathogens and irritants with you. And the lungs had to figure out a way to get rid of that stuff. So what it does, I didn't mention that these things, maybe I should say that first, these filamentous objects are called cilia, okay? And this is something that I discussed in the first lecture as well. So what happens in lungs is that your airways are covered by this thin hair-like filaments or cilia, and together again they beat in unison or in coherence, and their coordinated beating helps move pathogens back out of our lungs, keeping our airways clean. So this is a cartoon picture, but this is roughly what's going on inside our lungs. And these have important biological consequences, apart from like just as a collective phenomena that we are interested in, is that this is a clear indication of how important this sort of transport is. What they've done over here is that you're looking from a top view, and there is a whole bunch of ciliated cells, okay, underneath. These circles that you see, these are some sort of particles which help us visualize the flows of what's going on. And what happens is that you can see that these guys are beating, so there is a flow on the above layer, and these things are getting transported. But now once you're affected by COVID, this beating completely stops, and these pathogens or particles do not get cleared, okay? So cilia gets affected if you're affected by COVID, and that's why you're susceptible to a lot of secondary infections. This is another context where collective behavior is important, and this is something that I discussed in the first class. This is going back to the question of how we break the left-right symmetry in vertebrates, okay? So this is ciliated cells observed in the mouse embryo. There are about hundreds of such filaments, or cilia you would call. And what they're doing, they're beating vigorously. They're rotating like this. And they're coordinated, and the rotation is not random, they're all sort of coordinated. And their coordinated rotating patterns creates a flow from the right-hand side to the left-hand side of the embryo. And as we discussed, is that these sort of flows interact with chemical messengers on either side of the embryo that helps to break the left-right symmetry in vertebrates later on. And finally over here, I'm showing you a model organism. It's a chlamydomonas. It's a green algae. It has a pair of flagella, as you can see over there. And I'm going to use the word flagella and cilia interchangeably today because they're exactly identical for all of our purposes, okay? And what's doing is that it's performing what's called a breaststroke, right? It's just doing this. And this is actually held or squished between plates, but if you just allow them to swim, which you will see in the next slide, this guy will keep swimming. However, as you can imagine, if you want to swim, it's important that you have some sort of coordination between your right and left. You don't want things to be completely uncoordinated. And the question really comes about is how things are coordinated, okay? So in all these examples, the point that I'm trying to make is that more is different. And whenever you have more than one swimmer, or whenever you have more than one filament or one particle interacting through flows, you can have emergent dynamics. And in particular, in this set of examples, the emergent dynamics that I'm really hinting at is the role of synchronization. So in the first example, when you form waves, that's some sort of synchronization effect, that everything has a constant phase lag, that's why you have this traveling wave. Here you saw all the cilia beating in a coordinated fashion, that's a synchronization problem. And this is again, a synchronization problem of a chlamydomonas. Okay. So what I will do is that today I won't go to the n body or n particle problem, that's for next class. We're going to start with looking at sort of the hydrogen atom of our system, of our world, which is this organism of chlamydomonas. Okay. So what I will do is that I will show you some movies. and try to explain or pitch the problem that we are trying to solve. Okay. So let me first tell you that how these guys swim. So previously you just saw them things attached. They have this pair of flagella, as you can see, floppy flexible filaments. They're beating in a coordinated fashion and they're moving around. Okay. So this is again just to remind you, these are floppy objects. So these break time reversal symmetry. The beating patterns are not symmetric under the reversal of time, and that's why you have locomotion of these organisms. So what people did is that they would capture this organism by a micropipette. Okay, so you will just take sort of the setup over here and hold it at one place, so you're not allowing it to swim. And then you can image or study how they sort of, how this pair of flagella behave over time. So they're consuming energy, they're beating, but they're not allowed to swim. And you can see what happens to them. So we'll see. So of course, you see this synchronous beating pattern, which looks like the breaststroke. But you also see these sort of things that are going out of phase, or asynchronous beating patterns. And it turns out that if you observe this, do this experiment many, many times, roughly 85% of the time, you will see this synchronous breaststroke pattern. Roughly 10% of time, you will see this occasional asynchrony between these two flagella, which we're going to call slips, and I will explain that later on. So you sort of forget that you were in sync with your neighbor and do your own thing. And then the other thing that we are not showing over here is that for some periods of time, you can also observe drift of flagella, where you completely forgot that you were interacting with, and you do something very different from each other, and then again you get in sync later on. And that's what's sort of shown over here in these pictures. This is the synchronous breaststroke pattern. This is, clearly you can see that this is a series of time snapshots. This is the slip where you just forgot about that you were in sync. You do this once and then again get to this synchronous breaststroke pattern. And over here, it's sort of an antiphase synchronization. We're doing freestyle swimming. So this is breaststroke, right? And if you're doing something different, then you're doing this. So that's freestyle. That's freestyle swimming of these sort of organisms. Now the question is, how are they getting synchronized? How are they talking to each other? So that's the question that we want to answer today. And any guesses? So what sort of causing them to synchronize? Yeah.
Are they joined to the same position?
Okay, that's a very good guess. So I think the point that he's trying to make is that you have a cell, and then there are these two filaments coming together. They could be coupled where they're joined, right? They could be mechanically attached. So there has to be in sync, right? So the answer, short answer is yes, they are. There is actually a series of very complicated connections. They're not really joined. There is sort of a spring-like network connection inside the cell which couples them. That's true. However, what you can do, and I don't have movies for that, this is sort of an experiment that you can do. You can take one flagella from one cell and take another flagella from a different cell, okay, and bring these two cells together, which are now two distinct cells, and you can still see them getting synchronized. So that would be an ultimate experiment where you completely get rid of this internal coupling, if you have any, and you observe things getting synchronized purely by bringing them close together. So if that happens, what could be the other thing that's going on? Right, so this is another possibility, right? That's sort of a hydrodynamic mechanism where the flows, as the flagella is moving, is generating flows. And as it generates flows, it's going to talk to the other flagella, and that's causing the coupling. So what we'll do is that, I'll tell you the answer first, and then we'll do the calculations today. The answer is that it's really a combination of the mechanism that you suggested, the mechanism that he suggested. It's a combination of both. In actual cells, both of them are present. It's very hard to isolate these two things. But today we will discuss about the hydrodynamic mechanism and see how things couple. So the flavor of the problem, which relates to both of you, what you said is sort of synchronization of metronomes. How many of you have seen synchronizing metronomes? Okay. Some of you have seen this. Let me just play the movie, you'll see it again. So these are mechanical oscillators that are not in sync. There is a Coke can, there's a platform. As you put them together, the platform, if you notice, is swaying sideways. If you just wait long enough, they will get synchronized. And the reason this happened is exactly a mechanism like you've suggested, that they are attached or they are on a common surface, and this common surface is not perfectly rigid, it's allowed to move, so it's allowed to communicate the disturbances that they're generating. So they're all now mechanically coupled, even though they're independent of each other, and once you mechanically couple them, this can lead to synchronization phenomena. So we're going to think a very similar set of mechanical coupling. However, the coupling now comes from the flows that we generate. Okay. So now if I want to model this system, so if I want to write down a model for this problem, and we have identified some of the pieces. First is that we have identified, I'll just write HI for hydrodynamic interactions. Okay, that's something that we have identified. We know that these things are floppy. These are elastic filaments. They can deform in flows. We also know that these are oscillators. Okay, they're just oscillating things. So we have these three pieces of information, and maybe you can ask that if I want to write down a model of two oscillators, which are flexible filaments interacting through flows, how should we proceed? What to do? Is this an easy problem? Is this a hard problem? What's sort of going on? What's your intuition? So what do we need to write down, or what do we need to know to figure out how they are going to communicate with each other? Let's ask that question. We need to know forces on each other. Anything else?
How they individually behave.
Right, so how they individually behave. So when you say behave, I think one option could be that you're trying to figure out what are the flows that they're generating, right? That we need to figure out. We may need to know that as these flows are generated, these guys are going to deform because they are floppy objects, right? So if you take a flexible filament, pull it through the fluid, it's going to deform. So maybe we need to figure out deformations, we need to figure out what the forces that they generate, we need to figure out what the flows that they're generating, and then need to understand how they're affecting oscillations. So this is a non-trivial problem, okay? This is not an easy problem. But what we'll do is that we're not going to solve exactly this problem. By what I mean by that is, I'm not going to write down PDEs or equations for an elastic filament interacting through flows and so on, but instead, we're going to take a reductionist approach and try to write down the minimal things, or the minimal ingredients that we need to keep in a model to figure out how things interact. Okay. And for this, I'm going to propose something. Maybe you guys can say whether this sounds reasonable or not, which don't show you the result. So I'm going to say that, so let's forget about the cell body for a moment, because these are held fixed. I'm really thinking about motion or synchronization between flagella. I'm going to propose that flagella are spheres. Is this a good approximation? It sounds reasonable. Yeah, that's so. Does everyone know about the spherical cow joke? Yeah. Okay, right. So this is really the spherical cow approximation, because I can't solve this problem. This is the issue is the following, that I cannot solve this problem. This is just too hard. So I want to do a simpler problem, and in the simpler problem, I'm going to say that flagella. I'm going to model a flagella as a sphere. Does that sound reasonable? No, not at all. Let's see. Okay, so let's look at experiments. When you say something like this, we'll have to look at experiments. So what I'm showing you over here is a flow. So this is, again, just to recap, this is the chlamydomonas. This is not swimming right now because it's held, okay? But it's beating with a pair of flagella, and you just saw a movie where it was swimming, okay? So what you can do is that when an organism swims, you can put some small particles and observe how these particles are moving around. And then from that, you can try to infer what is the velocity field that these guys generate. Okay. There's a method, it's called particle image velocimetry, or short PIV, but that's not important. This is the flow field that you get out of that experiment. This is an incredibly difficult experiment to do. You have to do many, many times. You have to average, all sort of experimental details I'm not talking about. But you can do this experiment and compute this flow field, some orders of microns per second. And what you have is, here you have the cell body, right? Here you essentially have a pair of flagella beating, and this is how the velocity field looks like. Okay. So this is the system, right? This is roughly spherical body, flagella. And here is now my approximation. I'm now going to say that this is like an elbow, right? So this is doing this over and over again. This is like a joint. So I'm going to say that I'll put two spheres here. I'm going to model this as a sphere. Okay? So what it is doing when it's performing a breaststroke is pushing down on the fluid, right? It's sort of doing this, correct? So I'm going to push down on the fluid. I'm going to say that, okay, I will replace this whole complicated system with flexible filaments, a rigid body moving through fluid, hydrodynamic interactions, all these things getting replaced by just 2 point forces acting in this direction. And then a spherical body which doesn't do anything, it just creates a drag. This is what you're dragging. Okay, and this guy is moving in this direction.
They're not issues with symmetry.
Sorry?
Time versus symmetry.
So we are not trying to figure out how this guy is swimming. We are trying to figure out how the flow fields look like at any given instant. So to break things like time reversal symmetry, you need to add certain other things, which we'll do in a moment, and we'll see what that is. So this is this approximation, and it's sometimes called the three-sphere model. It's very evident why. And that's the solution to that model. Okay. And now you can say, or you can look, and now you can answer the question again, is replacing flagella by a sphere a good approximation? Still not convinced. So this turns out to be a very good approximation, at least in this context, right? It recapitulates the velocity field to a great extent. It captures that there is this sort of recirculating region, which means that if you put a fluid particle, it just goes round and round. It captures that there is a point over here where the flow doesn't move. So these are called hyperbolic stagnation point. It captures that. It captures the right circulation, captures a lot of things correctly. Okay. So what we'll do, yes?
So when particles making is flagella motion, the microorganism, so it's like it is taking up its flagella and dragging it. I mean, once it reaches here, then we assume no drag, right? Until it reaches here.
No, the flagella has drag all along, right? So as the flagella is moving, it's experiencing drag.
But what we have considered there, like, on the board.
So this is really a time averaged picture. So on average, this is how things are looking at, and that's how we are modeling it. I'm not going to say that this is the true picture, but I'm going to say that if this is a model, if this is how I'm going to model it, it better has some correspondence with experiments. That's the only point that I'm trying to make. And it's not horrible to do this.
So ideally, when it's going upwards, the drag is lesser, like it moves in a way so the drag is less, and when it's coming back, the drag is more. So that, like, on an average, it appears
Right,
like the drag is
right. You're right, exactly. So you're pulling yourself by performing this stroke. That's correct. Okay.
Shouldn't there be a point distribution of forces?
There should be a point distribution. There should be absolutely. That's absolutely correct. So what Pratik is mentioning is that these are distributed objects, and if there are sort of a distributed object, you would imagine that all points along the filament is applying a force. It's not just one point that's applying a force. So indeed, there should be a distribution of forces. Completely true. But this is my reductionist model, and I'm going to say that I'm going to drop all this distribution and say that this is just a sphere. It's really a model. I'm not going to justify it beyond that. It's a modeling choice, but a model that produces things that look correct. It's really my justification. So that's this piece, and
solved by simulating?
no, we will do it analytically. Yeah. So we'll do calculations today. Okay. So what we did by going through this, or not really going through this, but I just said that we'll do this and give you some crude justification for that. We sort of solved this part of the problem. Okay. What I mean by that is that I'm saying now things are spheres, and we know what kind of flows spheres generate. Okay, that's sort of known. People have solved that. So we have sort of got a handle on the piece of how these things can interact, how these things can generate flows. But let's ask the following question: what will be our handle on flexibility? Okay, so these are floppy objects, and how should we model it? Yes, so just to repeat, so there are three things that we are thinking of. First is that these guys are consuming energy and they're beating spontaneously. That's why they're oscillators. Okay. Second thing, these are flexible filaments, flagella, right? They can deform under stresses from the fluid. They're like strings. So that's flexibility. And the other piece is that as they move, they're going to generate flows. So we need to figure out what forces they're exerting on the fluid and what are the flows that they're generating. So what we have done is that we are saying now that whenever I have this filament that's moving in the fluid, I'm going to approximate this stuff by a sphere that's moving around and around. That will be my approximation. Okay. So I'll just draw now. I'll make this more clear in a moment. But this is my approximation for thinking about what are the forces and what are the flows that they're generating. But what is my approximation of what can I do about flexibility? Because they are floppy objects. What can I do about that? That's correct. So that's a very good suggestion. So one option could be that you can think of these as two rods, and that's some minimal model of flexibility. That's absolutely correct. But that's still too hard because solving for two rods is harder than solving for a sphere. I want to keep the sphere picture. Sphere can deform. Well, the size of the sphere really. So what I'll tell you the coarse-grained approximation. So say this is the length of the flagellum. The size of the sphere is really roughly the diameter of this guy. So it's like a bead. This is very small, very thin, and I'm not going to think about deformation of this object. What can we do? 2-3 beads, that's still hard. Can we do something simpler? Okay. Okay, trajectory needs to change. Great. So that's exactly the route that we want to do. So if we have a sphere and if it's deformable, I mean if this flagella is deformable, if there are flows, it's going to bend in response of the flow. And that can be like, it's not on a fixed trajectory, but you're allowed to go away from this trajectory. That could be the model. So, but then what you're sort of getting at is that if things were not perturbed, if things were rigid, then there was a perfect circular trajectory where this bead is going round and round. But now I want some deviation, but I also want it to be restored at this bead. I don't want it to go away, right? I want it to be on this orbit, but it can deviate slightly from the orbit. Okay, so that's correct. So we can put a spring, right? That would solve the problem. So let's do that, and let me draw this picture this way. So this is my circular trajectory. There is a bead, and I'm going to put a spring. Fine, okay. Roughly the radius of this circle, I'm going to take this as r, but r, you should remember, it's roughly the length of this flagellum. That's roughly my radius. That's my modeling choice. And the radius of this bead, I'm going to take to be a, and a is roughly the radius of this flagellum. That's right. Okay. And remember, a is much smaller than L. Okay. So this is correct. So this is K. So I know the length, I know the radius. So far I know these two parameters from measurements, from some experiments. What should be K? How can we estimate K? So it has to be tied to the rigidity of the flagellum, right? So what does the rigidity of a flagellum depend on? What does the rigidity of a filament depend on? Or what sort of the intuition is? It depends on what's called the bending moduli. What does the bending moduli depend on? Sorry?
How the molecules are arranged.
How the molecules are, okay. So the answer is that it's some material property. Fine. Which sort of makes sense because if I try to bend a plastic, if I try to bend a rubber sheet, if I try to bend a metal sheet, they will all bend differently. So the answer is it's a material property, right? And let me call the bending moduli to be B of this guy. And I will define what a bending moduli is, don't worry. And so Naveen has said it depends on the material property, so I will just write E. And E is essentially what you guys studied. Is called the Young's modulus of an object. Okay, it's tied to elasticity. It has dimensions of force per unit area. So now let's see why this is not entirely correct. Let's try to figure this out. So let's take this scale. Okay. Yeah.
Like you have assumed this, we have taken this spring length to be L, right? I mean,
Spring length to be L. Yeah, correct. The rest length to be L.
if we take spring length to be L, it can extend beyond L, right?
Right, absolutely. So you can deviate from this trajectory.
So what we are telling is like we can move away from the filaments like that, and I mean approximately the sphere.
So right, one idea would have been, I think what you're getting as is that you can think of there are many spheres, they're all connected by springs. That would be one model of the flagellum, if I understand that correctly, what you're getting at. No.
What I am asking is like you are assuming like the filament's motion to be like a sphere's motion to the fluid, right?
Right.
Yeah. So if you are assuming like that, like it should be like moving something like.
Okay, I see. The question is, the trajectory should really be like this. Is that it's like a line, it's like this. Is it? Or it should go right like this. What?
I think what he's saying that flagella can't extend its length. So in that case, like there should be upper.
Oh, that's correct. So absolutely, the flagella cannot extend its length. What it can do is that in response of a flow, is that if a flagella was straight, say, and you apply a flow to it, even without changing its length, it can deform. And what I'm saying is that any proxy for deformations, which is sort of deviation from this rigid trajectory, is going to be modeled by the spring constant K. It's again a modeling choice. So I don't think of it as the flagella being stretching and compressing really, but think of this as flagella deforming and changing its shape. That's my proxy for flexibility. Okay, again a modeling choice really.
If flagella was rod, then we won't put spring.
That's correct. So if the flagella was rod, we won't put a spring. Absolutely.
While it is rotating, it can wobble around apart. That's why we are.
Right, exactly. So coming back to this point, bending rigidity is proportional to Young's modulus. That's a right intuition because, like I mentioned, different materials would deform differently. But now let's take this scale, okay? This is the same material, or I will do two experiments. I'll try to bend it, okay? It's easy to bend, correct? Fine. Now I take the same scale and just change the direction, okay? The same scale, same material property, nothing has changed. Now I try to bend it. It's very hard to bend. You guys can try. You want to try? You have not tried. You have to believe me, okay? So it's not just E. There is something else sitting in this problem, and this something else piece is geometry. Okay, so it depends on how you're deforming things or around which axis you're deforming things. Okay, so let me just yes. So right, okay, so I have now clamped it. If you're thinking of a clamped object, then it's like a cantilever beam. The slight difference is that this thing is internally actuated, so it's doing its own thing, but it's one end is sort of clamped like a cantilever. You can think of it that way.
But isn't it actually symmetric?
So right, that's correct. Okay, that's a very good point. So this object is not like the scale, which is very different across two cross sections. So for this object, it doesn't matter around which axis I'm trying to bend. Absolutely. So that's actually symmetric. But what I'm trying to get at, I need to put something else here to make things correct. And I will just write this without justification. And you have to take it for now and just like make it I. What this I is called the area moment of inertia. Okay, I'm not going to define it, but this has units of force per area. This is units of length raised to the power 4. So this whole thing has units of Newton meter squared. Okay, that's my bending rigidity. Fine. So now let's ask another question. Suppose I take a rod with some bending rigidity B. Is it easier to bend a shorter piece of object or a longer piece of object? What's easy to bend? Longer. So we all have that intuition So if I want to say what the spring stiffness is, or effective spring stiffness is of this whole object, length of the filament should show up somewhere, because it's easier to deform long filaments compared to shorter one. Okay, and now I'm going to say that, you know, the units of spring constant, right? The spring constant unit is force per unit length, newtons per meter. I have a quantity which is tied to bending that has units of Newton times meter squared. And you guys have told me that it's easier to bend or deform long objects. So what should I divide or what should I multiply it with, which depends on length, to get some units of newtons per meter. So this is purely scaling, okay? I'm not doing anything rigorous here. What should I do? What can be K? K should be proportional to B. That's we understand, because stiffer it is, harder to stretch. So it has to be proportional to B. Well, what should I do to B to get units of newtons per meter? Divided by L cubed. Okay. So that's going to be my proxy for K. And what it really encodes, longer filaments, easier to deform. Rigid filaments, harder to deform. This sort of intuitively makes sense. Okay. And the good thing is, I know the length of the flagellum, I know the material properties of the flagellum, so I know this parameter as well. This is not some fitting parameter anymore. So I know K. So that's all the things that we need to know. So we know the radius of the bead, we know the radius of this undeformed trajectory, we know the stiffness of the spring, and we also know the properties of the fluid in which it is. So I know the viscosity and so on. Okay. So we know everything about this system.
When you solve the problem of three spheres, that time the two spheres are moving towards the object.
Correct.
So where is this circular trajectory coming?
So this flagella is tracing out a shape that looks like this, right? So I can think of this, that these guys are moving in a circle of the following form, where you have a bead. This bead is rotating round and round in the circle. That's sort of the approximation where the circle comes in. Okay.
Can you say that the circle would just be a phase map of how the...
Right. That would be a mapping. Absolutely, agreed. Okay, so we have essentially all the pieces of the problem. Now we need to write down equations to figure out what's going on with them. Okay. So there is one last thing we need to do to write before we write down equations. It's something that you have to sort of take for granted because it's hard to derive in this course. But I'll try to give you as much motivation as I can for that piece. So the following piece is, we know what is the drag on a sphere. We have done that. And I will denote this by zeta. This is 6 pi mu a. Of course, zeta times velocity is the drag force. Zeta is purely a geometric thing that depends on viscosity and the radius of the sphere. So this is like a Stokes drag thing. And you know the drag force, if the particle is moving with some velocity x dot, say, then this is 6 pi mu a x dot. That's the drag force. Okay. Suppose I ask the question that this particle is moving with a velocity x dot, but it's moving in a fluid which also has a velocity, or a background velocity, if you would like to call, which I call u infinity. So let me say what I'm trying to say here. So there is some flow happening. This is my flow, and there is a particle that's moving with some velocity x dot. Okay, and I want to compute what is the drag force on this particle. And just remember, there is a flow around it that's happening, and that's happening because it's externally imposed, say. Okay. So maybe I can phrase the question differently. When you think about drag, okay, does the absolute value of x dot matters, or is it the relative value of things that matters? Relative value. So we all have that intuition, right? So if I'm moving with the same velocity as there, I won't experience any drag. If I'm moving with a different velocity, there is friction, and that's why there is a drag. And probably, if I write this, hopefully this is not too bad. So I should have put a negative sign here. That F drag is really minus zeta So this is really what you can call in certain ways a first order approximation. I won't go into the details of why it's first order approximation, but is this roughly intuitive at least? That really what matters, the forces that are acting on you really depends between the difference of velocity with which you're moving with respect to the velocity with which the fluid is moving. That's sort of intuitive, right?
Why did you write U?
Oh, that's just a choice. That's just, I could have written it U if you want. Okay, it's U. This is a choice. I wrote it that way. There is no reason to write U infinity. Yeah.
Is this true only for constant velocities or accelerated phase?
There is no acceleration in Stokes law, right? So we have dropped accelerations. Yeah, these are all. There is another number we haven't talked about, Stokes number, which is related to particle inertia. All that is low. It's over damped dynamics. So the drag force is really the relative velocity difference.
If there is a variation in space.
Correct. So that's the piece that I'm not talking about. If U varies in space, right? Or U can vary at the scale of the particle itself. So this has some radius A, and the U may not be same here and here and here and here, right? It could be different. So that's absolutely correct. So then there will be another term showing up, but you can show that that other term is order A squared. So that's a higher order term, and that's why he said this is really the first order approximation to the problem. If there is variation of flows, there are more terms that will show up, but we are not considering them. It's too hard. Let's just stick with this. But roughly, is this intuitively okay? That drag forces depend on difference in velocities and not the absolute velocity. Okay, so with this, let's try to solve the problem. And by solve, I mean I will draw it again, and we will see what we are trying to do. I'll just erase this. And I'm going to make some geometric simplification because that makes the calculation nice and clean and we'll get nice results.
How the space variation term is in terms of, is it the adjective term?
No, so what the question is, so let me write that term. I'll mess up the signs. Okay. Let me just write this. Okay. What the question is that this velocity u, which is the external velocity, is may not be constant along the surface of the sphere, right? So different parts of the sphere can experience or sample different velocity fields. And the question is, if you have that variation, how does it look like? What does it contribute? And this is really the actual contribution. This delta is a Laplacian. It shows up as a Laplacian of the velocity field and proportional to the square of the radius of the particle. But if the radius of the particle is very small, this term is subdominant, so I'm not going to think about this piece, okay? So I'm not going to think about this piece, and all I'm going to think about is just u. Okay. So let me draw the picture. Picture is as follows, that I'm going to do some geometric simplification. Hopefully at the end of the lecture, you'll see why those are nice. But this is my trajectory. I'm not great at drawing, but let's see. Okay, this is trajectory. So we're thinking of a synchronization, so there has to be two things, not one. And these guys are separated by a distance that's roughly d. Okay. So there is a wall, okay, above which these two particles are sort of hovering, and the spheres, which are my model for flagellar, they're just rotating around these particles, around these parts. And of course, there is springs attached to it. I'm not drawing. So let's call this particle 1. Let's call this particle 2. And I need some axes. So let's call this x. Let's call this z. Let's call this y. So if I look at things on this plane and this height, they're also on a plane. Okay. So why they're at a height h from the wall? Why this is some sort of simplification? Because like I just drew here, the orbit, if you had been doing a phase map, as you suggested, this wouldn't be this simple. This would be some complicated shape, tilted at some weird angle, and this wall is sort of modeling the cell body, if you want to call it. So it's like an infinite wall. So it would have been something complicated, and that's hard. We want to do that. We want to do something simpler. Okay, that's why we're doing this.
The trajectories are on the xy plane.
The trajectories are on the xy plane, correct. Okay. So let me draw these things on the xy plane. So there is one particle here, and there is another particle that's here. Let's call this phi2, let's call this phi1. Yes, absolutely, absolutely. You can tilt it, you can do all those sort of things, and they just make the calculations fairly complicated. Okay, we'll do the simplest thing. And this is D. And remember, this is your x, y plane, okay. Okay, so let me ask one thing. Suppose, just let's consider this case for a moment, that these guys are perfectly rigid orbits, no flexibility, and suppose they're not talking to each other through the flows that they're generating. So then what will happen is that we can write down an equation for phi1 dot, and that's simply zeta times r naught, and r naught is the sort of the base length or base radius of the trajectory, which it will be if it is rigid, zeta times r naught times phi1 dot, and that has to be equal to a force that's driving these guys along the trajectory, correct? And this force, you should think about this force, is the force by the virtue of which this one cilia, one flagellum oscillates. Okay, as it oscillates, it's generating a force, and it's generating that by consuming energy, and this is my proxy for that force. So let's write that. This is just F. This force is always tangential to the path of the rigid circle. Is this okay? Yes.
Is it like the centrifugal force?
No, it's not like the centrifugal force. So again, there are sort of two pieces. This is counterintuitive. One thing is that the ideas of sort of centrifugal forces and things like that, these are again inertial ideas, inertial concepts. These are not there in Stokes' flow. The way you should think about it is that as the sphere is moving, it's experiencing a drag from the fluid. I know its velocity. The velocity is simply r naught times phi dot. So I know the drag that comes from the fluid. That is simply zeta r naught phi1 dot in the e hat phi direction, in the tangential direction, correct? But this has to be balanced by a force by which you're driving this, and that's this driving force F. This is also in the tangential direction. If you project things, you simply get F, or let's call this F naught if you will. F naught is simply zeta r naught phi1 dot. And from this I just get that phi1 dot, which I'm going to call omega, and this, as you can imagine, this is equal to phi2 dot as well. They're identical spheres, they're identical things, is simply zeta times r naught. Yes. Okay, that's very good. Okay, so this is really the crux of the problem. I thought that I will be able to slip this and no one will catch. Absolutely correct. So if you're thinking about chlamydomonas, which is this breaststroke, this particle should be moving in the opposite direction, not in the same direction. Okay. There's a twist to the story. So I will tell you about the twist at the end, what happens if they move in the opposite direction, but let's for now do the case when the things are moving in the same direction. Okay. So that's omega. Is this okay with everyone?
Still a little confused.
Sure, go ahead.
The forces and that children.
Okay, so oh, I'm sorry, I didn't write zero here. So can you repeat the question?
The
Okay, so the model is the following, that you have a rigid hoop for a moment, and you have a particle that's moving along the rigid hoop continuously, correct? So you need to apply a force in order to move it, correct? Now the point is that as you're moving along the trajectory, the fluid is going to resist your motion. So we know the drag force on the particle, and that is the Stokes drag times velocity. The velocity of the object is r0 times phi dot. Now this drag force must be balanced by the force I'm pushing it with, and that's my f0. Okay? Yes.
We haven't added this spring.
We haven't. We will add it. Yes. For now, this is just a rigid particle problem. Okay. So that's this stuff. So these, without the spring, without interactions, these two beads are identical. They're just rotating in the same direction, and they have an angular velocity which I'm calling omega, which is f0 over zeta times r0. Okay. So now let's write down equations of motion when you have a spring. Okay. So I will just write down equation for this particle 1. I won't write down equation for particle 2, but we'll just change 1 to 2 and you will get the same equation. So maybe I'd start by the most general setting, and you will tell me whether this is fine. Okay. So let me explain what I wrote down. This is equation of motion of particle 1. Okay. Zeta is my friction. Remember, zeta is 6 pi mu a. x1 dot is the velocity of the bead 1. Okay. What is this stuff, this u showing up over here now? Can anyone guess what this is? Flow due to sort of, so what I'm doing, yeah, go ahead.
Flow due to both the spheres.
Right, so it should be ideally flow due to both the sphere, but what I'm doing, I'm going to do an approximation. I'm going to say that this guy just feels 2 and 2 feels 1. So this is the flow induced by the other guy that's rotating in that orbit. That's u induced by 2 at 1. That's this arrow, that's what this means. Okay. The flow induced by this bead at the location of the other bead. That's u. Yes.
In this equation, the extreme velocity u infinity
Is u to 1. Yeah. Yes. So there is no external flow, but okay. So previously when I was drawing that picture of u infinity, I was saying that there is some externally imposed flow, and that's where the difference of velocity is coming from. Now there are no external imposed flow. However, you are a swimmer, so again you are swimming, but now there is another person swimming by you. So you're now going to sense the flows that are coming from this other person, right?
You should have done that there.
I could have done that here as well, correct. I could have done that here as well, I didn't do it. I just wanted to talk about omega. Absolutely. So this is really an isolated one particle problem in a rigid hoop. This is the ideal sort of case, correct. Is this okay? And F is all the F that's there in the problem. It's this tangential force, plus we will add the spring force in the problem. So let's write what F is. What is F? What are the things that go into F? Can anyone help or suggest what goes in F?
K square.
Half k square is the energy. So what does it go? Minus k times. So let's call it R1 minus R0. Fine. This is okay, right? And this is in which direction? In the in the r direction. So let's set up coordinate system. It's getting confusing. This is E hat phi, and this is E hat r. This is in the r direction. right? Okay? Yes? Oh, sorry, I didn't define this. So this radius is R1, this radius is R2. If you were the rigid object, if you were the rigid circle, the radius is R0. So instantaneously, your radius may not match with this R0. So the spring is trying to pull you back, right? So that's this stuff.
So the spring is getting reformed the same amount of length every time it's reformed, right? Because
No.
it's R1.
It depends on the instantaneous radius R1. R1 is changing with time. R1 is not fixed. Because R1 is now going to get influenced by the flows that you're sensing. So R1 is changing. R1 is a dynamic quantity. What is the other piece of force? F0. So there is F0 still, right? So let's call this. So this is there because this is driving things. This is why the bead is rotating at the first place. So this has to be there. Fine?
The origin of F0 is from the
So yes, so the assumption is that your consumption of ATP or consumption of energy has not changed. Okay, so you're still driving it with the original F0 that you had in the system. I'm not going to change F0. Okay, so I'm going to drive it with F0. Okay. Okay.
What is R0?
Okay. Suppose there is no spring and the orbit is rigid and you have a bead going round and round. Then this is R0.
R1 is same.
And now as the flow appears, what can happen? The bead can go outside, the bead can come inside. It can do all sort of things. And I'm saying at any instant, the radius of this circle is R1 of time t. Okay? What is x1 dot? What is x1 dot? Okay, let me write it down and we'll see whether that makes sense. Does this make sense? There is one dynamics in the radial direction, and then there's one direction in the azimuthal direction. That's R1 phi1 dot. That's my angular velocity, right? All good so far? So what now I can do is that I can project this equation in the radial direction and in the tangential direction, right? So let's do that. So let me write this down. So if I project it in the radial direction, I will get R1 dot minus U21 times E hat R minus, or maybe I just write this. That's the radial direction, okay? So that's a radial projection. I can also do this projection in the azimuthal direction, and that is R1 phi1 dot okay. Is this okay? This is just algebra. I'm not really doing anything. It's just doing it. Okay with everyone? So I can do the same thing for the other bead. I won't do it. You can do the same thing with the other bead. What is going to change for the other bead in these equations? What is the only thing that's going to change? R1 will become R2, or phi1 will become phi2, correct? These will become 1 to 2. Will these guys change? They will change, right? They have to change because these phi1 and phi2 are different things. So you can write down E phi just to make that very clear. E hat R is simply cosine phi x hat plus sine phi y hat, right? And the E hat phi is minus sine phi x hat plus cosine phi y hat. And this would depend on what the values of phi are, right? So these are different quantities for different particles. Is this okay with everyone? They're not same things. So these will also change.
Transform it to the new unit.
Right, we'll just have to write down ER and E phi in terms of say x hat and y hat in that new, with the new phi 1. So for this guy it will be just phi 1, for this guy it will be just phi 2. That's the only thing. Okay?
While we are solving for the problem, like, we should fix that one coordinate system.
Yeah, the coordinate system that we have fixed is x and y. So that's fixed.
And where is the origin?
Okay, you can pick the origin here.
Yeah, if I pick this to be the origin, then I have to pick like
But the unit vectors are not changing, right? I mean, your
x and y don't change.
yeah, but why will ER and EY, if he would change depending on the origin?
Yeah, like
Those are the unit vectors of the problem.
yeah, but if this is your origin. This should be your ER hat. Like if you're taking somewhere else, your R hat should be starting from the origin, right? Like it won't start from the.
So I'm defining if you're okay, if you're getting confused with ER and E phi, you should just think about them as tangent vector, normal vector to the trajectory. If you're getting confused with the name ER and E phi.
For this one it will be fine. For the second sphere, we are not fixing the center of the second sphere to be the origin, right?
Sure.
Their ER hat will be different from this one.
The ER and E phi should just depend on the angle. If I represent this in terms of x and y. So what I'm saying is, go ahead. Yeah.
It depends on the angle that makes it the origin.
That's not changing. That's x and y is not changing, right? This is my x and y. So okay, there is a vector which is like this, and there is another vector say which is parallel to this. And I'm only interested in the unit vector. It's pointing in the direction. They're the same unit vectors, right? The position vectors are different. If you're thinking about the position of the bead, that will involve dx hat plus this stuff. Correct. But the other piece is not changing. Okay. Okay. So that's this problem. So that's where here we are. Can we solve these equations, or if I write down the other ODs, can we solve it? There is one piece we haven't written down explicitly. Can anyone guess which is the piece? U. So we still don't know what U is. I mean, we kind of know because we said that these are sphere. And for spheres, people have solved for flows, so you know what the velocity will look like, but I haven't told you what U is. So I will have to tell you what U is. Okay. So there's another place where I will just tell you what U is, and then you show a movie how U looks like. Okay. So let me erase one piece. I have to erase one thing. Okay. Just erase this. So U. Let me see what's the best way to write this. Let's just write U2 to 1. No, let's write it properly. Okay. So don't ask me where it comes from. It's not easy to derive this actually. It's a non-trivial problem to derive it. You have to solve for a flow past a sphere, which is now against a surface of this form. So if you have done things like electrostatics, and if you think about electrostatic problems where you have charges above a surface, you need to think about images of the charges to solve the problem, right? So it's a bit like that. In this problem, if you want to solve it, you need to think about image system and so on. So it's a non-trivial problem. But this is what you get for the velocity field. And I will explain what it means. Go ahead. Sorry? It is related to x2, absolutely.
I mean, I was expecting a simple term with x2.
This is not very complicated, as you will see. It looks complicated, but I will make it simpler. So what is F? F is a force that this bead number 2 is exerting on the fluid. Okay? So think of it this way. If you're a sphere and you're moving in the fluid, you're going to exert a force on the fluid, and that's going to drive flows. So it sort of makes sense that the flow you drive is proportional to the force you generate. And the reason why it's not force squared, force cubed, everything is linear, is because the Stokes is a linear problem. Velocity you generate is proportional to the force you're exerting, and vice versa. Right? What is R? Well, R is x1 minus x2. It's just the difference of the position of these two guys. This is again a complicated mess, right? Because of this weird geometry, to compute it, it's hard. So I will just say this is x1 minus x. Yeah, this should be minus dx. Let's just make this. Let's make our life simpler. Okay, this is r. This r to the power 5 that's sitting over here, that's simply, this is really mod r. So this is just d to the power 5, nothing else. And it also depends on h. Remember what h is? H is how height or how far you are away from the wall. Okay. So let's write down what you get for u. So you get 3h square over 4 pi mu times 1 over d to the power 5. This r is again just nothing but minus d x hat. And I need to take a dot product between the force from the bead 2 and this vector r. Okay? Again, a messy stuff. We'll make simplifications. We have already assumed that r is roughly this. And we're going to further assume that, okay, the force does involve contributions from the radial piece and this stuff. But really, what is driving this dynamics is this azimuthal motion. The radial piece is just there to keep you in place. So really, things are driven because you're rotating the sphere. So I'm only going to take that azimuthal piece, and I don't want to make mistakes in sign, so let's see what comes out of it. Well, I hope this is correct. What you get is F naught times E hat phi for the particle 2 times d or negative d E hat x. Right? That's what I get. And E phi for the particle 2 is simply minus sine phi. I mean, if you take a dot product between E phi at particle 2 dotted with x hat, we'll just get minus sine phi 2. Let me just write this. So then becomes minus 3h square over 4 pi mu times 1 over d cubed plus 7 phi 2. Correct. So that's correct. Okay. So this is just plus. Is this okay with everyone? What I did?
Does one thing interact with the other with the wall, like?
Yeah.
Or directly pushes them?
So it's of course sort of directly pushing it because they're on the fluid, but the flow that you're solving for does incorporate the fact that there is a wall. Okay, so that's what you get for this guy. Okay, so that's U21. Any more questions on this? This is just algebra. I haven't done anything, and what I will do is that if you don't follow this algebra, it's just bunch of calculations. I will send you out the notes so you can see the algebra yourself. Oh, sorry, you're right. F naught should be there. I'm sorry. F naught should be there. Correct. Okay. Okay, so now I have an expression for U2, and I can plug it over here, and then try to manipulate these equations. Okay. So I mean, I'm sort of tempted to do the whole calculation. So let's keep doing. We'll stop when we need to stop. Okay, so we have U21. What we can now do, let me just erase this piece. Let's use this expression over here. I can simply multiply with these vectors and derive equation for R1, so R1 dot, and we can derive an equation for phi1 dot, correct? So I will just let you do the algebra, but I will just write down the equation that you get for R1 dot, R2 dot. But let me, okay, let's do this way. So what you get is the following. Is minus k over zeta times R1 minus R naught. And then if you do this calculation, it comes out to be beta R naught omega sine phi2 sine phi1. Okay. So where did this stuff show up from, R naught omega and what beta is? Well, you just remember that F naught, I have a relationship for F naught. We know that F naught divided by zeta times R naught is omega. So F naught can be written in terms of omega times zeta R naught. That's the first thing that we did. We were thinking about the rigid hoop problem. So I know F naught in terms of these things. What beta is really a purely geometric parameter that depends on h and the distance d. It's some combination. I think I have an expression for beta. The beta is really 9h squared a by d cubed. So it's a geometric parameter, and the fact that there is an a showing up is the fact that zeta is 6 pi mu a. So if you do a bunch of manipulation, that's where this parameter comes from. But that's one equation for R1. And I can also derive an equation for phi1, so, or phi1 dot, if you would. So which looks like the following, that R1 phi1 dot is equal to R naught omega plus beta R naught omega sine phi2 sine phi. That's the two governing equations that you get. Okay, so you can also write down R2 and phi2, but it seems like this is all that we can do. We have derived ODs, now you need to open MATLAB or Python, put these ODs in, solve and see what happens. But we can do a bit more, okay? We don't want to go down the route of solving this in MATLAB or Python. What we want to do is that we want to make more approximations and keep making approximations till get something that's analytically treatable, okay? The idea is as follows. What is the dimension of k over zeta? Can anyone guess? Just from this equation. Can anyone guess? It's 1 over time. It's 1 over time. Okay. So k over zeta is 1 over time. It's called tau. And it turns out, I know k, I know zeta, right? So k is b over L cubed. That's what we derived. We also know zeta, which is 6 pi I know all the numbers for these things from experiments. I know B, I know L cube, I know A, I know viscosity. I plug everything in, and what I find is that if you put the right numbers, you find that tau is order 10 to the power minus 3. Okay? So it's tau itself is an extremely small quantity. It's a very small number. And the reason it's a small number, or the intuition is that, well, the orbit is really stiff. So it really doesn't allow you to go away from its rigid object. It just allows a little bit, little modulation. But that's this number tau is. Okay? So now how many of you got a chance to read the notes that I sent? Some of you did. So now if I write tau as a small parameter in the problem, I can simply massage this equation and write it in the following form, which is, so k over zeta is 1 over tau. So I multiply things, so I get something like tau times dr1 dt is minus r1 minus r0 minus beta tau r0 omega. Let's write things. Sine phi2 and cosine phi1. So this is exactly like the ODE that we solved in the notes. This is epsilon times dx dt is some order one thing times epsilon times some forcing. And we don't need to solve this ODE. We can sort of guess what the solution or the approximate solution looks like, right? And the approximate solution, as I mean, this is done in the notes, so I'll just write the expression. R1 for all time, you can approximately write as this R0 minus beta R0 omega tau sine phi2 cosine phi1 plus order tau squared. So this is really my solution to R1. Okay. So this is a perturbative approximation to what R1 is. And of course, R1 is changing. So, okay, if this term was not there, R1 is equal to R0, which is a rigid approximation. But because of this stuff over here, R1 can now modulate, and it's changing with time because phi1 and phi2 are changing with time. But the great thing is, I know what R1 is now. I don't need to think about this equation because I've sort of solved this equation. I know what R1 is. And then I can plug R1 in this equation and simplify and get an expression only for phi1 dot. I've got rid of R1 in the problem. Okay? Phi2 is still there, yes. So you have to do this exact same steps for phi2. You have to do all the same steps for phi2, but what we'll do is that once you write an equation for phi1, you'll immediately see the symmetries in the problem. All you need to do is to change 1 to 2.
These were coupled, right? Because
they're all coupled, they're both coupled. And I mean, these terms are arising precisely because of coupling. Because an equation of phi1 now depends on what phi2 is doing, right? So I won't do the steps, but you can sort of see where this comes from. You do these approximations, and let me erase this stuff. And what we get finally is the following for phi1. Yes?
How did that one become more a process?
Oh, okay. So this is an equation which is of the following form. Epsilon x dot is something like minus 1 minus x in this problem, or what did I write? It's sort of 1 minus x plus epsilon times some function, right? And what you can do to solve these sort of equations, you can do a perturbation expansion in x in order epsilon, and at each order of epsilon, you will solve the problem. So at leading order, x is just equal to 1. At order epsilon, you will get another term, and at order epsilon squared, you will get another term, and so on. What I'm doing is that I'm just retaining terms up to order epsilon, which is tau here in this case, and neglecting all terms that are order epsilon squared. That's what I did. Okay, so let's write down what we get for phi1 dot. It's sort of, okay. So it's, let me write down then explain. Beta minus tau sine phi2 cosine phi1 plus beta omega sine phi2 sine phi1. And phi2 dot, will anyone like to guess what phi2 dot will look like? Correct, okay, so you got the trick. Okay. So just ignore these terms for a moment. You want phi1 dot to be omega and phi2 dot to be omega, right? That sort of makes sense. If you don't have any interactions, if things were perfectly rigid, you want them to be just doing what they were doing in isolation. So all these terms arise, is sitting there. Yes, okay. All these terms are sitting there because of interactions between them. Of course, we have to do this sort of big calculation to get to this point. Okay, so what we can do is that when you're interested in synchronization, you're not really interested in the evolution of one guy. But what we want to compute, what's the evolution of the difference of the phases, right? Where does phi1 minus phi2 go? Correct? So let's just do that. So let's subtract these two equations and define this thing, delta, to be phi1 minus phi2. What do we get for delta dot? So these two omega would cancel out. These term will cancel out. Does everyone see that? They are sine phi2, sine phi1, this is sine phi1, sine phi2, so these will cancel out. So I'll just get this piece. So what is this sine phi2 cosine phi1 minus? Okay, let's do this. This is beta omega squared tau sine phi2 cosine phi1 minus sine phi1 cosine phi2, right? What is this? It is sine phi1 minus phi2? Okay, so maybe if I want to write in terms of delta, what should I do? Okay, so I can put this. Okay. So all these calculations to get to this point, really. Okay, so this is what we want. What are the parameters in the problem now left? Okay, there is omega, fine, omega squared. Who cares about omega? Let's think about beta. Beta is a geometric parameter, which was something like 9 square a by dq. Do we care about beta? We kind of do, because if you want to take the limit d to infinity, beta is 0. So if they're really far apart, they're not going to talk to each other. That sort of makes sense, right? If you're really two oscillators sitting really far apart, they're not going to talk to each other. So beta would be 0. So beta is really controlling the strength of the coupling, but it controls purely through geometry. This is purely geometric factor. It depends on how far away from the wall you are. It depends on how far the spacing is. This is geometric factor. What about tau? What is tau? Tau is zeta over k. Right? So now let's ask the following question. We did all these things, but now I take the limit of my spring constant k going to infinity. What does that mean if my spring constant goes to infinity? It's a rigid rod, right? So if it goes to infinity, there is no deformation. What happens if k goes to infinity? Tau goes to 0. So you have two spheres rotating on rigid orbits. They're talking to each other through the flows they're generating, but their phase is not going to change. It's going to remain fixed. So tau is absolutely crucial. And you can see why it's extremely important to have some flexibility in the problem. If it's a rigid stuff, it's not going to synchronize. So I will leave you a puzzle at the end of the lecture, is to figure out, without doing any calculation, why rigid particles cannot synchronize. And of course, the hint is of time reversal symmetry. The argument is sort of convoluted, but if you draw pictures and try to reverse time, do reflections and so on, you can prove without doing any calculation that two rigid spheres can never synchronize in Stokes' law. Okay, so tau is absolutely crucial. Okay, now let's ask the following question. There is some interaction. The delta dot is going to evolve. Are they going to synchronize in phase, which means phi1 minus phi2 goes to 0, or whether they will synchronize anti-phase? How will you figure this out? How will you figure it out? So where will it go? In phase or anti-phase? How to figure out where this system goes at time goes to infinity? How to figure that out?
Find the fixed points.
Sorry?
Find the stable.
Okay, find the stable fixed points. How will you find it? Del dot equals to 0, okay. I mean, that will just tell you that delta is n pi. That won't tell you about the stability of the points.
It means we depends on the initial.
Does it?
Add a small phase difference and see how it evolves.
Okay, add a small perturbation and see how it evolves. That's the way to do stability. But can we do it by just drawing things? How is Akshit doing stability? Phase space, okay, phase space. What is the phase space of this problem? What's the dimension of the phase space? It's 2? What is the OD? What's the variable? Okay, it's a 1D problem. So let's draw this. This is delta. And let's draw delta dot. Okay. So if my constant, so let's draw what sine looks like. Okay. So this is how sine looks like, right? This is 0. This is pi. So on. This is plus sign, right? How will the minus sign look like? Right? Beta is positive, omega square is positive, tau is positive. Everything is positive, and there is a negative sign instead in front of it. So now you tell me, whatever be the initial condition, where will I end up? Yes, so wherever I am, this is the direction I'm going. Right? Any perturbations from 0 will bring me back to 0. Right? So these guys are going to get phase locked and get synchronized. So now you see that you have two flagella that are floppy, that are talking through the flows that they're generating, and they will eventually get synchronized purely through hydrodynamic interactions. There was nothing else in the problem. Of course, if you change the sign of epsilon, or I didn't say epsilon, of this quantity sitting over here, you will end up being at pi. And being at pi means you're anti-phase. So this is in phase, and anti-phase is this. Okay? When will we be anti-phase? Okay, how to change the sign of this quantity? Can we change sign of beta? Can we change signs of omega? Can we change tau? Tau has viscosity. Maybe we can make viscosity negative. No? So now this goes back to what Nitesh was saying earlier. What if the spheres were going in the opposite directions? Because in CLAMI, these two spheres, and let me just repeat what Nitesh was saying, is that you have these two spheres, and I made them go like this, correct? But if you're a flagella, you're doing this, the spheres are going really in the opposite direction. So you can do this whole calculation by saying that spheres now go in the opposite direction. And we'll see that you'll end up with a plus sign over here. Okay? And that's a problem. The problem is that in experiments, we have observed that things are beating in phase and in synchrony. And now there is a conundrum how to resolve that with this stuff. Yes?
I quite didn't understand the problem. It's a plus sign and pi works out.
Right, so you will go to pi, correct? But once you go to pi, that means that these two beads are anti-phase, they are not synchronized. Now you're doing this. There is a phase lack of pi between these two guys and not 0. So this thing which was performing this synchronized breaststroke is now going to perform freestyle swimming. So it turns out, this goes back to your point at the very beginning, is that there are additional things in the problem. It's just not hydrodynamics. There are couplings coming from the places where they're anchored, very much like the metronomes. Like the metronomes were talking to each other, these guys can also talk to each other. And those couplings actually drive them towards in phase in this clamming case.
So if you remove one flagella and put it in another, you see antiphase.
So, okay, it turns out there is the reason you can take a mutant of Chlamydomonas. The mutant is called PTX1. So Chlamydomonas can do phototaxis, these guys cannot do phototaxis, and these guys do not have this networks of coupling. If we perform the experiments with them, that's consistent with this picture, and they exactly do freestyle swimming. They don't do breaststroke, they perform freestyle. Okay. So now let me.
So this model we haven't really accounted for the inside the cell coupling.
No, we haven't done anything of that sort. Correct.
We see that in case such a thing, if we can incorporate that into the model.
Yes, we can.
Then we can say that antiphasing might be
Absolutely, absolutely. So, can you help me with the projector? So let me do one more thing before I show you experimental results. We did all this calculation to get to that point, but what is a physical reason for why synchronization is happening or why this is happening? I mean, of course, this sort of tells you that you need flexibility, you need hydrodynamic interactions and so on, but can we do something of this sort where we just draw pictures and figure out how things can synchronize between each other? Okay, so let me just do that. So now say that there are these two particles rotating on these circular orbits, and one guy is lagging the other. Okay, so this is the phase of this guy is leading and this guy is lagging. So in order to synchronize and synchronize in phase like we have predicted there, this guy needs to speed up, right? You need to speed up and catch up with this guy, correct? Otherwise it could also slow down, absolutely. So now let me show you how the flow fields, this U21 that we computed, we wrote an expression for U21, how does that flow field look like? Okay, so to visualize the flow field, I can just draw what you call streamlines, essentially vector fields or arrows that tells you which direction the fluid is going at any instant of time. So let's look at that flow field. Okay. So this is one particle, or one sphere rotating on this circular trajectory. As it is moving, it's pushing fluid, and we want these arrows that you're seeing over here is the direction at which the fluid is moving. Okay, so let me play it. Okay, it's very choppy because of Zoom. But let's okay, great. Hey Bhagwan. Okay. Let me just stop it here. And let's go here. Okay. Okay. So this is this guy, right? And which direction it is pushing the flow? Which direction is the flow going? This direction. So if there is another particle here, it's going to get pushed by the flow, right? So this particle is going to get pushed out of this orbit because of the flow. The flow is trying to push it away. How about the other particle? If the other particle is here, right? That's where we drew it. That's where we drew it. Which direction is this particle affecting this guy? So think about this particle which is here. How is the flow being generated? No, so this is the left guy, this is the right guy. So if this is the flow, this is the right guy. Where should I put the arrow of the flow on the left guy? It's this direction, right? Okay, so the flow wants to push this guy out of the circle and this guy inside the circle. But remember, there is a relationship that R times phi dot is roughly F naught, right? So if I reduce my R, my F naught is not changing, that's my driving force. My phi dot, my angular velocity should increase. So as I move inside, my R has decreased, so I will speed up. This guy, so move outside, he will slow down, right? So through the slowing down and speeding up, these guys are going to move together and eventually get phase synchronized and phase locked.
Isn't that the half of that the top is outwards?
That's correct. But you know, I mean, the other particle is sitting here, not there.
But they're separated out.
Absolutely.
So if you draw the diameter over here,
They're separated over here, and you can extend this flow field throughout this region, and this region the flow is still going to be like that.
yeah, but it's like the radius if you extend it this way.
Which radius?
The radius in the second one.
Yeah,
You extend it this way.
I extend it this way, correct?
So the particle is above the.
If the particle is above here, then this particle is leading, not lagging. Then the scenario is reversed, right?
No, but here you see that the diameter passing through that object. The left side, the top side, the flow direction changes.
Correct. But the particle is sitting here, right?
Even on the left.
Even on the left, correct. I agreed. So, I mean, it's you have to do the math for that, which we did. But this is the rough argument, right? I mean, if your particle is here, you won't slow down, but you will slow down even further, you will fall back even further, but soon enough, you'll be like this. And then again, things will be pushing you away or pushing you in. Okay?
So what if those particles are starting at like
Exactly same position?
not exactly same position, but like in the same upper half or whatever. Of the
Okay.
Yeah.
So if they're starting in the upper half, this argument still holds.
But both of them are getting pushed out, right? But
It will take some time, exactly. It will take some time to get to that point. Correct. So the other way to think about it is that I didn't talk about this. So delta dot is some constant, alpha times sine delta. If you solve this ODE, which you can solve, you will see that the solution is like exponentials. So if you start very close, you're really on that sort of plateau where you're slowing down and getting synchronized very slowly. If you start very fast, the evolution curves looks like this. So if you're starting really here, you're going to be just being there for a very long time. And remember, the strength of the flow also depends on how far they are away from each other, right? So it has a 1 over d cube things. If you're starting close to each other, then yeah, the strength is sort of there. Okay, this is flows above a wall, which the problem we did. You can do this in free space, and you can draw pictures, do the same argument, and you will get to see the same thing. Okay, so we are getting late. Maybe I will start off from here next time, but let me just tell you the point that I'm trying to make now. We did all this calculation, and there were many approximations. We said that flagella is a sphere. Then we said that they are really far apart. The distance, I will approximate certain things to make my algebra simpler and so on. We said something about elasticity, a lot of approximations, and the question is, how does it compare in experiments? If you try to measure something like this quantity alpha, which is a strength of coupling, how does it compare when you compare to actual experimental values? Unless otherwise there is no point in doing it. And what you're seeing over here is measurements over thousands of periods of beating of these two flagella, and you're plotting this delta, the phase difference. First thing you should notice is that this is a noisy system. This is not the perfect curve that you expect. When delta is not changing, these are periods of synchrony. When things are beating in phase, they're phase locked. And then there are these jumps, as you can see. And the jumps are exactly like this. You're doing this, and then suddenly you did this, and then again you're doing this. So jumps is places where you're gaining sort of this extra phase. And the other thing is that even though there are jumps, but there is a bias in which direction this delta grows, right? And then something disastrous or bizarre happens over here, where they have completely forgotten each other. The delta is sort of changing as random, and they got phase locked later on. So this is a really noisy dynamics, and we didn't put any noise in our system so far. Okay. So what we will do is the next time is when we start is that we'll first put noise in the problem and see how we can interpret this dynamics as dynamics in some potential landscape, and figure out when things will hop and when things will not hop. And then what I will do is that I will start with this two particle theory that we derived. Then say if there are not two but n particles, what's the evolution equation looks like. Okay.
Why is the delta increasing?
Why is it increasing? That's because this is another assumption that we made, is that we said that the frequency of these two oscillators are identical. They're both omega. It turns out here their frequencies are slightly different. Okay, there is omega 1 and omega 2, they're slightly off. And there is a systematic difference. So this flagellar beats systematically faster compared to the other guy. So even though there are slips in either direction, so you can increase and decrease in either direction, but overall, since there is a systematic bias, the phase sort of drifts in one direction. And this becomes extremely evident once you write down or recast the problem as a particle in a potential, which we'll do next time. But let me just close with a punchline. We'll go over this last time. So what people did in these experiments is that they went back, took this movie, and fitted this equation to the stage where they're synchronized. Okay, they really fit this equation. They compute what alpha is. Okay, and they're calling it epsilon, the same as alpha. This is the experimentally measured values. You see a peak there, and this is the theoretical prediction that comes from this model that we just calculated. And you see that they're falling extremely close to each other. Okay, in biology, things are fairly noisy. I mean, this is really as good as it can get. That you make a prediction with so many approximations, which starting of things like saying flagella is a sphere, we met so many approximations, yet we were able to get something that sort of, I would say almost quantitatively, close to what you observe in experiments. Okay. And we'll discuss what happens when you cut the flagella, when flagellar growth happens and so on. There are various ways to test these predictions. I will go over that next time, and then move on to n particles. Okay? Okay, thanks.